Hi everyone, good morning again. This is my second talk, transition parameters for neutral magnesium. We have to think first the magnesium element. You can see that the picture of the magnesium. Magnesium is a chemical element with the symbol Mg and atomic number 12. It's the shiny gray, you can see also in the picture, solid which bears a close physical resemblance to the other five elements in the second column, group 2 or alkaline earth metals of the periodic table. All group 2 elements have the same electron configuration in the outer electron shell and a similar crystal structure. So the outer electronic shell is so important for us. I said you the previous talk that we have to think about the open electronic shell to find that the transition parameters, because these electrons are the active electrons for the oblique. And this element is the 11th most abundant element by mass in the human body and is essential to all cells and some 300 enzymes. It's so lots of, you can see these number. Magnesium ions interact with polyphosphate compounds such as ATP, DNA, and RNA. Hundreds of enzymes require magnesium ions to function. Magnesium compounds are used medicinally as common laxatives, antacids, milk of magnesia, and to stabilize abnormal nerve excitation or blood vessel spasm in such conditions as eclampsia. Yes, from the medicine also, from the medical part, yes. And also you can see that the physical properties of the magnesium, melting point density like this on the left side you can see, and the right side you can see that the stable isotopes, yes, and the it has that the stable three stable isotopes, yes, you can see here the atomic the mass number, yes, the mass number, also the different mass number, but atomic number is 12. And also you can see that the electronic configuration, yes, 2262, and the total you can see that the 12, 12 electron. So the periodic table, you can see that the magnesium in the group 2, 2A. So the 12 is the atomic number, and we can see here also the same program. Yes, we use the same program with the silicon and HTAC atomic structure program, and we found that the oscillator strengths and transition rates of the transitions. So you know that these multiple transitions are so important to understand the transition probabilities, and we have to find that these transitions with these methods. Sometimes we can use that the many-body perturbation theory and sometimes configuration interaction method, and then we can compare the results. So this program is suitable to find that these different methods results. So you can see that the non-relativistic Hamiltonian, it shows that the kinetic energy of the electron, potential energy between the electron-proton interactions, and also the other potential energy, electron-electron interactions. So this is a non-relativistic Hamiltonian, and lots of atomic programs, atomic structure programs, you can see that the non-relativistic calculations, but in this program, with using this program, you can find that the non-relativistic and relativistic Hamiltonians result with together. So for this program, we have to think about the fully relativistic configuration interaction approach, RSIM, It means that this method follows the flexible atomic code methodology. In this section, the theory of the fully relativistic configuration interaction approach, RCIM, configuration interaction approach, yes, you can see this method, CIM, is briefly described. The bound states of the system are calculated in the configuration mixing approximations with convenient specification of the mixing chain. The radial orbitals for the construction of the basis states are derived from the modified self-consistent Dirac-Fock-Slater iteration on a fictitious mean configuration with fractional occupation numbers representing the average electron cloud of the configurations included in the calculation. The next one, the R matrix theory. R matrix theory is a calculational tool based on scattering theory by deriving scattering properties from the Schrödinger equation in a large variety of physical problems. Its principle relies on a division of the configuration space into two regions, the internal and external regions. The boundary between these regions is defined by a parameter known as the channel radius. The detail may be found in many sources, as you can see. And also the multi-reference many-body perturbation theory approach, the numerical procedure of this method follows Wilkes et al. And Ishikawa et al., starting with Rayleigh-Schrödinger perturbation theory for a multi-configurational model space. You can see that HPC, EPC, yes, you can see here. So we can use that this approach to find that the parameters. So in details, maybe if you want to learn that this part in details, you can see that the reference and these research papers, and then you can find that lots of information. And you can see here that this is the program, and this side, yes, I show you full relative and non-relative, full relativistic part and non-relativistic. So we have two options to find that. So we can find that the full relativistic result and non-relativistic result, and also we can compare this one. I said you the last talk, the previous talk, we mostly compare the experimental part and the theoretical part, and also we have to compare the full relativistic and non-relativistic part. And for this study, we found this relationship between, and we compare between them and compare. So you can see that the initial configuration, we can write that, first we can write that the electronic configuration of the atom, and then we can write that the initial configuration and the final configuration. Yes, we can think that the transition, the lower state and the upper state, yes, we know that the properties of the lower state, for example, J, this is the angular momentum, the total angular momentum of the electron, yes, from the fine structure, and also we know that the energy levels, and also for the upper levels. So with the experimental techniques, we can find that the absorption or the emission, and with the theoretical part, we can compare this one, okay? This all possible lines for the theoretically we can find, and the experimentalist find that the results, and then we can compare again, okay? So you can see that the result for the non-relativistic method, we found that the oscillator strengths and transition rate, and also reduce multiple matrix elements. And for the, you can see here the magnesium, and also the next one about the relativistic Hamiltonian. These results show that the relativistic Hamiltonian, yes, we choose this option and found the result. So you can see here that the different results, and we can compare that. Yes, you can see the delta E show that the difference between the lower state and the upper state. So these are same quantities, yes, for the relativistic and non-relativistic, but the other parameters depends on the transition probability, and the transition probability related with the lifetimes. Yes, you know, so these properties is the characteristic of the atoms. It depends on the electronic configuration at the atom. So we have to solve all the atoms, all the ions, and also for the also all the structures. Yes, we can find, we can use this program and find the result. So we can compare this one, for example, for the transition rates. Yes, you can see that 6 point like this, and 5 point, and 1.8, 1.802, and you can see that the result is increasing for the non-relativistic and decreasing for the relativistic parts. Yes, we can compare this one. And also for the reduced multiple matrix elements, yes, we can find that these result for this one. And the oscillator strengths, yes, oscillator strengths, you can see that this difference. So if you want to know that, you know that the Hamiltonian for the non-relativistic, yes, also I show you again. Yes, it's a simple, basic, pure Hamiltonian. Yes, kinetic energy and potential energy side. But the relativistic Hamiltonian, we have more terms and we have to add and solve these interactions. Okay, so it's so complicated. So sometimes we use that non-relativistic calculations to find that result to find that result easy. Easy, but for the real one we have to do the relativistic calculations and find that. So we can compare with these results, and also the aim of this work is to determine oscillator strengths of the neutral magnesium atom, the atomic number of the element magnesium given by its configuration 1s2, 2s2, 2p, 6. This side you can see that the closed shell, but the third shell will look at 3s2, but the p not electron on the p, d not electron on the d orbital. So this is the open shell. So this shows that interaction. This shows that interaction. So the atomic number is 12. We determine transition energies and oscillator strengths of neutral magnesium using HTAC program, which is comprehensive code that enables performing atomic calculations. In this study, we calculated theoretically energy levels of the magnesium 1 and oscillator strengths of 35 spectral transitions in the in the 255 nanometer to 270 nanometer wavelength range, which are experimentally unknown. So this is the first time. So we can compare this site for the theoretical part, yes, for the different methods with the different methods. So you can see the references in this site. And I think I completed, yes, maybe the result you can see again and then compare. I think I said yes, the important theoretical parts here. Yes, you can use, with using this program, you can find oscillator strengths, transition rate, and you can see that the transition probability is for the atoms. Yes. So thank you very much for your attention. Have a nice day. See you.